In this video, part 2 of chapter 6.2, Finding Antiderivatives Analytically, we're going to continue with our examples. So example G, we have 1 over 2t minus the square root of 2 times e to the t. All right, this 1/2 is just a coefficient of 1 over t. So we can look at this as the integral, 1/2 the integral of 1 over t, minus the square root of 2, the integral of e to the t. All right, that integral turns out to be 1/2 the natural log of the absolute value of t, minus the square root of e to the t plus c. Letter H, we're integrating the sine and the cosine. The integral of sine is negative cosine, so we have negative 4 cosine x. The integral of cosine is positive sine, so we have plus 3 sine of x plus c. 1 over cosecant. Cosecant is a reciprocal function. It's the reciprocal of sine, so 1 over cosecant is equal to sine, and the integral of sine is negative cosine of x. Okay, in letter J, we have the integral of the secant squared. Okay. The integral of secant squared is tangent, so we have 4 tangent of x. Cosecant x times cotangent x is the derivative of negative cosecant of x. All right, letter K. Distributing, we get secant squared x plus secant x tangent x. The integral of secant squared x is tangent x. The integral of secant x tangent x is secant x. Letter L. We're going to rewrite this, breaking up the numerator into 3 terms, 1 over x squared minus 1 over x plus 3 over x to the 3/2. The first and last terms we can rewrite as negative exponents with negative exponents before we use the anti-power rule. Okay, so we're going to get negative 1 over x minus the natural log of x plus, that should be a negative exponent, 3 times x to the negative 1/2 and then we're dividing by negative 1/2, which is the same as multiplying by negative 2. Okay, so for this one, I'm going to simplify a little bit. We're going to call this negative 1 over x minus the natural log of the absolute value of x minus 6 over the square root of x plus c. Letter M, let's distribute again. Secant of x squared, and secant and cosine are reciprocal functions, so their product is 1. Oops. All right, secant squared of x, we can antiderive with the tangent of x, and 1. Antiderive 1, you get plus x, plus c. All right, letter N, we have sine of x over cosine squared of x. If we rewrite this, breaking it up into sine over cosine times 1 over cosine, that is the same as the integral of tangent of x times secant of x. The integral of secant x tangent x is secant of x. Okay, letter O. We have sine of 2x over cosine of x. Trig identity for sine of 2x is sine of x times cosine of x times 2. So simplifying this expression, the cosine of x terms can drop out, and we're really integrating 2 sine of x dx. The integral of 2 sine x dx is negative 2 cosine of x plus c. All right, in the next examples, we're looking at the graph of f here on the left, and we're going to note that f is equal to f prime. So we're supposed to sketch an accurate graph of the function f, which is the antiderivative of the function little f. You are also given that f of 0 is 0. So already we know the starting location for this function. All right, remember the integral of f of x dx is going to give us the area under the curve. We're going to look at the integral from 0 to 1, the integral from 1 to 2, the integral from 2 to 3, and the integral from 3 to 4. Okay, so thinking of those areas, this is a negative 2. So this triangle has an area of 1. And it's going to be negative because it's below the curve, below the x-axis. Here's a positive 1, and a negative 1. So the integral from 0 to 1 of f of x dx is negative 1. The integral from 1 to 2 is 1. The integral from 2 to 3 is 1. The integral from negative 1 to 4 is negative 1. If we look at the sums, here the integral from 0 to 2, we'll be looking at 0, and the integral from 0 to 3, we'll be looking at 1, and the integral from 0 to 4, we're back to 0. So we're going to plot these values. Negative 1, 0, 1, and 0. All right, now some other things that you can tell about your function because you are looking at the derivative. We know our function is decreasing and increasing and increasing and decreasing. Okay, so capital F of x is behaving according to those increasing and decreasing. We also know that because the derivative has a positive slope from 0 to 2, that f is concave up on this interval, and from 2 to 4, since little f has a negative slope, we know that the function capital F is concave down. All right, so drawing a graph where it's decreasing and concave up, increasing and concave up, increasing and concave down, decreasing and concave down. Capital F of x would look like this. All right, it says sketch the graph again when f of 0 is 1. Okay, well, what that would mean is that for every one of these values, I'm going to add 1 to the value we got for the integral. So I could look at this as 1 plus the integral, 1 plus the integral. All right, that's just going to shift my curve 1 unit up. The shape of the curve will remain the same, where we have increasing and decreasing intervals, concave up and concave down intervals. Okay, so two different initial conditions, two different graphs, but they have the same shape and they are just vertical shifts of each other. Okay, so we've been looking at the indefinite integral, the integral of f of x dx, where we're looking at lowercase f as our integrand, is the function capital F of x plus c. Okay, so little f is the derivative of big F. All right, how is the integral of f of x dx different from the integral of f of x dx, where we have these values for a and b? Okay, those are called the limits of integration. All right, and they describe the interval on which you are finding the integral. So, for example, in that last picture that we just looked at, where we were looking from 0 to 4, those were technically our limits of integration. And we could have said the integral from 0 to 4 of little f of x dx. Okay, if the graph goes on forever and ever and ever, okay, I would still, according to that, we call this a definite integral, just be finding the area under the curve on the interval from 0 to 4. Okay, all right, we're still going to look at some indefinite integrals that have no limits of integration, and I'm going to let you do some of these on your own, because they're reviewing some of the simple rules, a power rule, e to the x, trig functions, 1 over x, negative exponents. And we will pick up our next video with evaluating the definite integral.